Right, so this is the last lesson in the unit. And this is a lesson that's looking into a very specific type of exponential function and their very specific type of logarithm. That's it. I start with this equation, which is not an exponential function. It's exponential-ish. Well, it has an input, a variable in the exponent, but also has that same variable in the base. So as x changes, both the variable and the base change. That's it. Let's just complete the table by substituting different values of x in. For example, when x is 1, this function is 1 plus 1 over 1, which is 2 to the power of 1. So 2. When x is 2, this is 1 plus 1 over 2, so 1.5 to the power of 2, which is a little bit bigger than 2. It's 2.25. And if you do the same thing for the rest, for example, when x is 3, you get about 2.370, around each of these at 3 decimal places. When x is 4, you get about 2.441. When x is 5, you get about 2.488. So notice, as x gets larger, as the input gets larger, the output gets larger. Not a lot. 2 to 2.25 and 2.370. So also notice as x goes up by the same amount, the output goes up, but by less and less. Right? From 4 to 5, it only goes from 2.441 to 2.488. And so that's it. Let's now start jumping into larger amounts. When x is 10, okay? No surprise, what comes out is a bit larger, but it's 2.594. Okay, let's jump from 10 to 100. We call these going up by orders of magnitude, multiplying by 10 each time. So when x is 100, we get 2.705. Still 2 point something every time. When x is 1,000, we get about 2.717. When x is 10,000, we get about 2.718. When x is 100,000, we get about 2.718. So notice all along as we put larger values in, we got larger values out, but it's making less and less of a difference. By the end, I'm getting 10 times larger, and you can see already at this point, there's no point. If I substitute a million into the equation, I know if I round to 3 decimal places, I'm going to get about 2.718. So it keeps getting larger, but it's getting larger and larger by less amount. And so that number, 2.718, is really, really important, especially going forwards. Just a little bit in this course, but really, really, really crucial going forwards. So first of all, as x gets infinitely large, right, as x approaches infinity, which just means basically what we've been doing, just keep putting larger and larger numbers in. That number is approximately 2.718, right? We've already seen that, but it's exactly e. Now that number e is not 2.718, it's approximately 2.718. Just like pi is not 3.14, it's approximately 3.14. And just like pi is an irrational number in that the decimals go on forever with no pattern, same thing for e. I know it must be approximately 2.718. I can see already, just from the table I made, that the 3 decimal places, the larger and larger x gets, it's still always around 2.718. But I also know I can never actually substitute x with infinity. There is no largest number. And so I can never actually reach this number exactly, but I know it's about 2.718. Again, an abstract idea. And we call this number Euler's constant. And is in a similar way that pi is kind of a strange number when you first are introduced to it in elementary school. And I don't think pi seems so strange to you now. It's an integral part of all secondary level math. E probably seems a little strange to you right now, but it is an integral part of so much of post-secondary math. All right, this is probably the first time you've seen it. And it is such an important number going forwards, especially in calculus, that the logarithm of base e we use a lot, and we call it the natural logarithm. And the abbreviation is ln. So there's 2 kind of special logarithms. There's a common logarithm, which is log base 10. I've already mentioned that. And then there's this one, which is the natural logarithm. And ln stands for natural logarithm. I believe it goes back to French. So the natural comes second. That's it. In English, we tend to get kind of lazy. And instead of saying natural logarithm, we just say ln, the ln of x. It's not called ln, it's called the natural logarithm. But out of just sheer laziness in the English language, we tend to just say ln. Okay? And so, like I said, in this course, it's not a big part. It is absolutely crucial going forwards. Okay? The log base 10 is not very useful when applying calculus to logarithms, the natural logarithm is very, very useful, and it's very pleasant. That's it. This is not a calculus course, so I don't want to go too much into that. So right now, let's first just get a sense about what this represents. So again, e is not a variable. E is a constant. And so e to the power of 0 equals 1. Again, anything to the power of 0 equals 1, as long as that variable is not 0. And again, e is not a variable. E to the 1.5, you can just go to your calculator. And I encourage you at this point to go to your calculator. And almost certainly, the way your calculator is set up, and there must be an e button somewhere, and usually it's set up to have whatever you type in go in the exponent. So on most calculators, once you find that e button, whatever you type next will automatically be in the exponent. So e to the 1.5, you should get about 4.482. And again, I don't really care about that number. I do care how to use your calculator. E to the negative 1, means 1 over e. And just to make sure you know how to decimalize it, you could just type in e to the negative 1. You should get about 0.368. However, I can also apply exponent laws. So for example, right here, I can write this as e to the power of 5 raised to the power of 2. So e to the power of 10. That's the exact value. If you want to decimalize it, you get about 22.026. But that said, as long as you know how to use your calculator, I don't care about any of these particular decimals. And then that said, this whole unit is really about connecting exponential functions to logarithms and understanding that relationship. Well, these are all exponential expressions with a base of e. So these are all logarithmic expressions with a base of e. So the ln of 3 means log base e of 3. That said, your calculator almost, if it's a scientific calculator, it has a ln button. And just type in ln of 3, and just to make sure you're using your calculator properly, you should get about 1.099. The ln of 1, I don't need a calculator for. This means, the log base e of 1, which means e to the power of something equals 1. Right? Well, e to the power of 0 equals 1, so this must equal 0. Again, not wrong to type ln of 1 into your calculator, but I know it's going to equal 0. Similarly, I don't need a calculator to know what ln of e is going to equal. And again, this means the log base e of e, which means e to the power of something equals e. Well, that must be 1. As well, though, log base e and e are inverses of each other, so they cancel each other out. So it makes sense that we're just left with something simple like 1. And finally, the ln of e to the power of 3 means the log base e of e to the power of 3, but the key is, and I'll write that down, but eventually I'm hoping, honestly, I don't encourage you to, every time you see the natural logarithm, to write it as log base e. It's never wrong, but I encourage us to eventually try to just get used to just dealing with the natural logarithm. That's it. I can use my power law, because again, the natural logarithm is clearly a logarithm, so I can rewrite this as 3 times the log base e of e. And again, we've already seen how that cancels out and is the same as 1, so I know this must equal 3 without actually using a calculator. And again, ideally, sooner than later, we can bypass this sort of step right here. And when we see a natural logarithm, we know it's the logarithm of base e, and we don't actually have to write it down every time. That's it. It's never a bad idea to write it down if you're unsure. And so now let's work with it. Let's solve an exponential equation and a logarithm equation, both dealing with e or log base e. So let's look at this exponential equation. I want to solve for x. Okay, x is in the exponent with a base of e. First thing I want to do is divide both sides by 200. Just get 1.5 equals e to the x over 2. Next, I always have a choice. I could log both sides. I could ln both sides. I'm just going to write this in exponential form. Sorry, it is an exponential form. I want to write this in logarithmic form. Right, so it's an exponential form. I want to write it in logarithmic form. And so in logarithmic form, this is log base e of 1.5 equals x over 2. That said, we could have maybe skipped that step, because everything you see right here is the same as the ln of 1.5, or the natural logarithm of 1.5. And again, our goal is to sooner than later skip right from here to here. That said, at this point, I can just multiply both sides by 2. and I have my x. So I can see x equals 2 times the ln of 1.5, or 3/2. And that's it. That's all I really care about. But why don't I go to my calculator? 2 times the natural logarithm of 1.5 is about 0.81. All right? But again, the most important part is definitely not that number, 0.81. It's understanding how we can solve this exponential equation that has a base of e. And so it's not surprising if we're dealing with an exponential expression that has a base of e, at some point we're using a logarithm of base e, which is the natural logarithm. And so here I have an equation, a logarithmic equation, involving the natural logarithm. So it's probably not surprising that at some point I'm going to deal with an exponential equation with a base of e. That said, what does this mean? If you want, you could write this as 2 times log base e of x equals 0.048. That's what this means. And so to solve for x, first thing I would do is divide both sides by 2. And so I get log base e of x, or the ln of x, equals 0.024. And now I'll write this in exponential form. So this is e to the power of 0.024 equals x. And again, there's actually my exact answer. But just to make sure we know how to use our calculator, that's about the same as e to the power of 0.024. Decimalize it, you get about 1.02. And so notice, maybe I'll just draw these arrows here. Actually, I'll just label it right here. Not surprisingly, at some point in this question, I took something in logarithmic form and put it in exponential form. And like I keep saying, it's never a bad idea to write ln as log base e, but just don't think you have to. And ideally, we can just skip that. Again, especially if you plan on taking a calculus course, you'll be dealing with the natural logarithm way more than log base 10 or any other base, to be honest. All right, so that leads me into this equation here, which again is something that's really important going forwards. Not a big part of this course, but we call this a model for continual growth. And continual growth really just means growth that is continuous, or exponential growth that's continuous. It doesn't go in steps, it's a continuous curve. And any exponential growth that is continuous, that doesn't go in steps, it literally just is one continuous smooth curve, can be modeled with this, where a naught is your initial amount, e, again, is not a variable, e is e, about 2.718, r is the rate of growth or decay, and t is the time in whatever units are appropriate for the question. And it's all about the context of the question. Now, this formula here, to prove how this works, to prove where this comes from, we actually have to know some differential calculus first. And so this is something that, again, we will just use a little bit in this course, becomes a major part of future courses, and that's where I can actually prove it. That's it, let's just work with it. So I start with some information about private money lenders. So these are not banks, they are private companies that lend out money to people who most likely banks would not lend money to for financial reasons. So private money lenders make it easy to take out a short-term loan, but if you read the fine print, which most people don't, they often charge around 50% interest, annual percentage rate interest. That's compounded daily. Okay? Some private lenders in the United States, on a side note, can charge in excess of 400% annual interest. In Canada, we have laws against that. But that's just a little side note. Okay, so let's go with the 50%, which again is not unusual. 50% interest compounded daily for a private money lender in Canada. So with that said, let's create a continual growth model to show how long it will take for a loan to double if you're being charged 50% APR compounded continually though. Okay, so I do say right here that this, in most money lenders, they compound daily. That said, the difference between compounding daily, which would lead to a really messy equation. For example, if you were compounding daily, this equation would look something like your initial amount times 1 plus 0.050, oops, not 0.50, 50%, divided by 365 to the power of time times 300 years and 365, right? If we were compounding daily, we'd have an equation set up like this. It's totally fine, just a bit messy. If I set it up using a continual growth model, which I'm going to do in a moment, using this idea right here, this, it's not quite the same. It implies that it's being compounded every instant, and every instant there's an infinitesimally small amount of interest being added. So again, it's one of these weird abstract ideas, but it ends up making almost no difference in terms of how close it is to this fairly messy equation. And there's group problems we explore about that sort of connection. So what I want to do is use this equation up here to create a continual growth model. And so in general, I'll start by writing this down. A equals A naught times e to the RT. So A naught's my initial amount. I don't tell you what it is, so I'll stick with A naught. E is not a variable. The rate of growth is 50%. So R is just 50%. And it's actually not wrong to write 50% here. It's a little bit weird. It's not wrong, because 50% means 50 divided by 100. That's what 50% means. That symbol means divided by 100. That's it. 50 divided by 100 is the same as 0.5. So everything I wrote up here is correct. I'm going to stick with 0.5, which is just 50% as a decimal. But again, it's not wrong to write 50% as long as you put the percent symbol and you know what that means. But personally, I like that better. Times time. Now I know the units for time here must be in years, because my percentage is 50% annual percentage rate. Okay, so I know my time is in years. It's all based on whatever the percentage is. That's it. I want to see how long it takes for my initial amount to double. So from A naught to 2 times A naught. And notice how much cleaner this equation is compared to 1 plus 0.5 over 365 to the power of 365t. This and this, well, actually especially this part right here, this and this are almost equivalent. The difference between compounding daily and compounding continuously is really, really, really negligible, and yet this equation with e is so much more pleasant to work with. Okay? But what it means is, this literally means, what I wrote down here means this 50% is not compounding daily. This 50% interest is compounding continuously, which means every instant, and instant is almost 0. How close to 0? Infinitely close to 0 in terms of time. So every instant, there's an infinitesimally small amount of interest being added. Right? So again, really abstract, but is almost identical to what we got for compounding daily. With that said, let's solve this. I can just ignore the A naught or divide both sides by A naught, and I just get 2 equals e to 0.05t. And now I can take this equation in exponential form and write it in logarithmic form. And so in logarithmic form, this is log base e of 2 equals 0. Oh, I keep putting 0.5. Should be just 0.0. Should be just 0.5t. Not used to dealing with such large interest rates. That's it. I can even skip this step. Log base e of 2 is the same as the ln of 2. So I can even just get straight to here. Ln of 2 equals 0.05t. That's also in logarithmic form. Same equation. So now I just want to solve for t. Divide both sides by 0.05. And so I can see the time it takes in years is going to be the same as the ln of 2 divided by 0.5. Look at this. I just keep writing 0.05. Just so unused to using a 50% interest rate. Okay? So in the end, that's all I need to do. Ln of 2 divided by 0.5, which is about 1.4 years. And again, I'm not making up this information here, so using a private money lender, that whatever you borrow, if you don't pay anything back, the interest rate is so high that in less than 1.5 years, the amount will double. All right. With that said, let's get to a final problem. Similar idea. Final problem. So the image above is from a website of a short-term loan company. Okay, one I found in Canada. Use the information given to predict the APR, to predict the annual percentage rate that is used to calculate this loan. Keeping in mind the interest is compounding daily, but for in terms of ease and practice, let's imagine it being compounded continuously. All right, and it'll make our calculations much simpler, and it'll be almost identical answer. I'm not saying the work is simpler, but the calculations will be simpler. So again, what do I see here? I see that if I want to borrow $2,000, I'll pay $198.50 once a month for 18 months. So this website I found, to make it really easy to show you, you can literally slide this bar around and show you how much you want to borrow, how much you have to pay back, but never does it actually tell you easily what the actual interest rate is on this website. And I mean, you have to like read through tons and tons and tons of small print, really small print, to find what the interest rate is. Because if you look here, they don't actually tell you what the interest rate is. It is compounded daily, but we want to imagine it's compounded continuously so that we can use that formula I just showed. But what's the interest rate are they charging? So first, the interest rate, I want to know annual percentage rate. So I want to think in terms of years. And also I want to think about, okay, I know I'm borrowing $2,000, but how much are we actually paying back? We're paying $198.50 for 18 months. So let's figure out what that is. $198.50 times 18. So it's $3,573. So first of all, that is the amount of money we're actually borrowing. Oh, not borrowing, sorry. That's the amount of money we have to pay back in total. So this is the total value of our loan after 1.5 years. And I'm thinking in years instead of months because, again, I want my interest rate to be the annual interest rate. That is the standard for all banks and loans and everything. Okay, so I can now go back to this here, this A equals A naught times e to the power of RT. And I know the final amount of this loan is $3,573. I don't know, oh sorry, I do know the initial amount was $2,000. E is E. I don't know the rate of growth. That's what we're trying to figure out. But I do know the time. It was 1.5 years. If I put 18 here, it's not wrong in terms of my calculations, but what I'll find out is the monthly interest rate if it's compounded continuously. And again, no bank talks like that. That's always annual. And again, I literally asked for the annual percentage rate. And that's how I know I want to think in years. That's it. That's not that messy of an equation. And so divide both sides by 2,000, and you get, I'll just leave it as a fraction. So 3,573 over 2,000 equals e to the 1.5r, or 3, 1.5, 3 over 2r, whatever. I'm now want to put this in logarithmic form. I'm going to try to go straight to the natural logarithm. So this is the same as log base e, or ln, of 3,573 over 2,000, and that equals 1.5r. Now, again, I went from exponential form to logarithmic form. If anything about what I just did here seems a bit strange, then you should probably add one extra step, which is literally to write log base e of all of this. Okay, like I keep saying, I'm trying to avoid that just because eventually, I don't know, it's kind of annoying to write steps I don't have to. But if, like I said, if this, what I showed here seems a little too much, then just add that extra step. And so my r, all I got to do now is take all of this and divide by 1.5. And so r will be the same as the ln of 3,573 divided by 2,000, all divided by 1.5. And this time I definitely do want to decimalize it because I want to know what the interest rate is. And you get about 0.39. So that means now I know this website, this company, was charging about a 39% annual percentage rate on their loans. They nowhere did they make that clear. And before I go on, if I was to solve this literally compounding daily, it would look something like this. My equation would start like, I'll put it over here. If I really was going to show this compounding daily, it would still be 3,573 equals 2,000 times 1 plus the interest rate, which I don't know, divided by 365 to the power of 365t. And t we know is 1.5 years. So if I wanted to solve this literally compounding daily, I would have to solve this equation. Okay? And I could do it. This time my r is actually not inside the exponent. But I don't know about you, and it is kind of, I guess, a matter of opinion. I really prefer the look of that to the look of this. And the answer you'll get will still round to 39%. Okay? So with that said, yeah, I like this better. All right? And before I wrap up, again, the key idea is that everything I got introduced today is just an introduction. We don't go in depth at all in this course with this, but it is absolutely crucial going forwards. Okay, we will rarely deal with any other logarithm but the natural logarithm in a calculus class. And why that is the case, well, you have to take a calculus class first. With that said, done the lesson, done the course.